Okay, I'm going to share screen with you guys. There we go. You should be seeing that now. You guys see that? You see the sigma over psi? Everyone
Yes.
see that?
Yes.
Okay. Okay, how's everyone doing this morning? Everyone's good?
Good.
Thumbs up? Okay. Today's lecture is going to be kind of deep in the materials theory and material science. And for some of you with materials backgrounds, it could be review. And for others who maybe come from some different backgrounds, it might be a little bit abstract and theoretical. It might not be very aesthetically interesting, I think. But this is important because we've talked about materials and light weighting and materials and geometry, and that you need to handle the material side, you need to handle the geometry side in order to get optimal structures. And so this first part, first couple of months of the lecture, first couple of weeks of the lecture are on the material side. So stay tuned if you're interested in more kind of maybe the more aesthetically pleasing part of this, which is the geometry side. That is coming in a few weeks. So I'm going to do my best to describe this today. If you have any questions, please let me know, but it's kind of a complicated topic. So we talked about maximizing the yield strength to density ratio, designing materials actually, not just picking materials out of a table, but actually designing materials where you've maximized the strength to density ratio. And we've talked about materials as systems, and to go down. Okay, we've talked about choosing overall material systems. Do you want to use aluminum? Do you want to use beryllium? Do you want to use steel? Do you want to use carbon fiber? That's it. Those are all systems, picking the material system. We talked about goal setting. And we talked about microstructural features and how, these different microstructures are systems, and how we can have these various systems, these material subsystems and microstructures at our disposal to design new materials that have higher strength to density ratios. In the previous lecture, I had an image right here. I don't know if you can see my cursor or not. I hope you can, but we had an image right here for martensite, which maybe wasn't all that great. And one of the students who isn't here today, he mentioned, what does this really look like? So I replaced this with a better picture of martensite. So this martensite shows all these little laths or needles that are kind of nasty interlocking things. And this is a very strong, necessarily tough, but strong material. But the systems we talked about were these laths and martensite. We talked about precipitates. We talked about inclusions, grains, and grain boundaries. These are all material subsystems that we can engineer or put together in different combinations to engineer a material that has a higher strength to density ratio. At the foundation of strengthening metals, at least, are these things called dislocations. And dislocations are a missing column of atoms. Okay, the top here, we've kind of shown this in 2D. You've got a 2D lattice of atoms in blue. The next picture over here to the right, we have one of those columns missing, okay? And that forms what's called a dislocation. You get like a half plane of atoms. And if you calculate the strength of a material based solely on the atomic forces, like how much does it take to pull atomic forces apart or slide atoms past one another, and you take that calculation and you scale it up to a full material, the theoretical material would be much, much stronger than what the reality is. Real materials are nowhere near as strong as that theoretical calculation of how strong a material could be. So scientists, maybe 50, 60 years, 70 years ago, maybe further than that, tried to understand what was the reason for this. And they found that materials deform by this missing column of atoms, because you can transport this missing column of atoms over the atoms next to it, let's say, or over other parts of the lattice. And that's how you really deform materials. And on the top here, I've shown like how you've got this dislocation and it's moving through this lattice of atoms, and you end up with a material that's elongated. And it takes far less energy to move this dislocation along this plane than it does to really move atoms apart if there was no dislocation. And this reduction in energy well accounts for the actual difference between reality and calculations. We can also think in terms of 3D. What does an atomic lattice look like in 3D? And that's what I'm shown kind of, I don't know, schematically here in the bottom column or that bottom row. And the reason I bring this up is because I want you to start thinking of dislocations as not just sort of, one-dimensional or two-dimensional things, but actually a three-dimensional thing. It's a line. You can have a line of dislocations that moves through a crystalline lattice of atoms. And what's really interesting to me personally is that even if you have like little tiny, piece of aluminum or something that's maybe only centimeter by centimeter by centimeter, you can have thousands of kilometers in that little cube of dislocation line. That's how small these things are. So really small. We talked about, I think this is where we stopped off, or right around where we stopped off last time. We talked about, we were going to go into some of the strengthening mechanisms and how can you slow down or make it more difficult for these dislocations to move through a lattice of atoms, which if it's difficult to move this dislocation through the lattice, that's the same thing as strengthening the material, because it's not necessarily going to deform by moving the atoms without dislocations, because that takes way too much energy, but how can you make it more difficult for these atoms or these dislocation lines to move through a lattice of atoms? Last time I think we talked about work hardening. This is a method by which you have all these millions or whatever, thousands of kilometers of dislocation line, and you tangle them up with one another, and you make it really, really difficult, really high energy to move these dislocation lines through the material. And that increases the strength in the bulk or the far field when you have a completed material, not just a bunch of atoms. I think this is the last slide we discussed last time. We talked about solid solution strengthening, that when you form an alloy, you have iron and you add, I don't know, chrome, or carbon. You have copper and you add zinc. You form an alloy. You take two different materials together, where the sort of the majority holder of all the volume is the solvent, okay, and then the little things that you're putting in there, the secondary elements you're putting in there, the solute, okay. Sometimes I'm going to call the solvent the matrix. It's the same thing. We talked about that's how an alloy works. You form what's called a solid solution, where different atoms take up different places in the atomic lattice. In the case of what's called a substitutional alloy, you have the solute atom taking up locations that are at the normal lattice points, lattice locations that the solvent atoms would be at. And then there's an interstitial solid solution, where the solute atoms are so small that they take up places in between the atoms. And we talked about how the place where they take up the spaces in between the normal lattice sites, that's an interstitial solid solution, and you can get higher strength out of a interstitial solid solution than you can out of a substitutional typically. And even more important, as you add more solute, you take up more interstitial locations and you can increase the strength even more. The example of a material that's an interstitial is steel. It's carbon in the interstitial positions in the iron lattice. And then we also talked about brass, which is copper with zinc atoms that take up lattice locations. That's a solid solution substitutional. So there's been a lot of work done to understand, like, if we have this atom and this atom, one's big, one's small, they're about the same size, whatever it is, how do we predict, this is a tool if it's predictive, how do we predict whether that atom is going to take up, that solute atom is going to take up a lattice position or somewhere between the normal lattice, the normal atoms? How do we determine that? Because if we can determine that, then we can design materials that take up interstitial positions, because that'll get us more strength. And it turns out that the size of the atom has a lot to do with it, as does the valence. So the number of electrons to get to the inert electronic shell configuration. So I think this is the first new slide for this week. Precipitation hardening is a very, very effective method, very potent method of strengthening materials. It's a very nice, convenient, potent, effective way to design materials that have stronger strength to density ratios, yield strength to density ratios. When you have, for example, the example I'm showing here is an aluminum. This is a 6061 aluminum, which is a solvent of aluminum. And then it has alloying elements of magnesium and silicon. Those are the primary ones. There's some other ones in there. But if you get a piece of aluminum, 6061 aluminum, that's not heat treated from your I don't know, aluminum processing plant. It has a microstructure which has an equilibrium microstructure which has these aluminum, basically it's an aluminum matrix or solvent, and it's got little particles in it that are these other combinations of elements that are alloy elements and solvent atoms that combine together to form these little particles. That material has some level of strength to it. If you want to increase the strength, one way to do this is to take that material and heat it up to what's called a solution treating temperature. For this aluminum, it's about 500 degrees Celsius. And what happens at that temperature is that the atoms that make up these little particles that were in there before, we talked about the raisin in the bread scenario, those little raisins dissolve out, and the atoms, because there's so much heat and there's so much movement in this lattice structure because it's hot, these little atoms move to different locations in the lattice, and you end up with a solid solution at that temperature, at 500 degrees Celsius. If you take that material and you cool it down very slowly, with time, you'll end up with the same thing you initially had. So you'll end up right back with the same raisins in the bread, okay? Now, if you quench that instead, if you cool it down really, really, really quickly, the atoms don't necessarily have time to move to where they had been before to form the raisins, okay? They don't, it's called diffusion. They can't diffuse there quick enough. So you end up with this material that looks very similar to what it was at the high temperature, but at the low temperature. That structure is locked into position. But, okay, locked is too strong a word. That material, when you get it back down to room temperature, say, is what they call metastable. Metastable, which means that if you give it long enough, it'll change to something else on its own. It could be that the raisins grow back. Some early aluminum researchers found that if they took this alloy of aluminum and magnesium and silicon, and they let it sit around in their lab for too long, that what it would look like on Monday morning was very different than it looked on Friday afternoon, because the material had changed. It was only metastable. There's thermodynamic forces there that cause these little precipitates to grow out of the matrix, to grow out of the solvent. And these could be aluminum silicide particles. They could be aluminum magnesium silicide particles. But typically, when you're running an aluminum facility and you're producing aluminum to sell to people, you don't have time for that to happen. You want it to happen quickly because then you can get more product out the door quickly and get money. So they invented what's called artificial aging. They found that if they heated this quenched aluminum up to a intermediate temperature, around 300 degrees C in this case, let's say, that these little precipitates would grow out. First, very, very fine, very, very fine. They go a little bigger, a little bigger, a little bigger, a little bigger, and then at some point they got so big that the material wasn't very, very effectively strengthened. Your raisins turned into dates, and it wasn't very strong. There's a point there where the precipitates hit an optimal size, the size where they provide the most strengthening. So these particles originally start out as little tiny nucleus that grow in the lattice of these aluminum atoms, right? And they grow. They're really tiny. They're so tiny that you can't see them with an optical microscope. In fact, by the time you can see the precipitates in aluminum with an optical microscope, you're already too far. You've already got dates instead of raisins, and the thing is too weak. Okay, so as these things begin growing, these little precipitates begin growing, the atomic planes of the precipitate line up with the planes of the aluminum. Okay, they call that a coherent precipitate. And these things grow, they grow with time and temperature. With time and temperature, they grow. And it gets to the point where they no longer can stay, the atomic planes can no longer stay the same. They can't line up anymore between the little precipitate and the matrix material, the solvent. Okay, and it's at that point where they become what's called incoherent. And when they're incoherent, they lose coherency. They are no longer as effective at strengthening. And that's where your material is what's called overaged, and that's where you want to stop using it. So this is a very real effect. I can't remember if I already told you the story, maybe it was last semester, but for example, I was responsible for an aluminum machine component once that was a housing for a motor. And this housing was machined at my company, and then we sent it to another company that put in the motor. They inserted the motor into this aluminum housing, and the housing was made out of a 6061 aluminum, And what they did is they had this sort of stack of steel laminates and wires, and then they put the armature down in there with a magnet in it, and that's how they formed the electric motor. But they had to make sure that this stator, this motor stator, would stay fixed in the aluminum housing. So what they did is they heated up this aluminum housing, and then when it was hot, they jammed in the stator, the motor stator, and then they let it cool back down. We get this part back, okay, and then all of a sudden we start having failures. These motors are blowing apart, and we don't know why. It turned out what happened was that when they were heating these things up, heating the housings up, the people who were doing it were letting it sit in the furnace, you know, at whatever, maybe 80, 90 degrees Celsius, 100 degrees Celsius. They let them sit in this thing for like up to 6 hours. You know, they didn't, for some reason, this motor company didn't really know that they could destroy the aluminum by doing that. So what was happening is while these aluminum motor housings were sitting in this furnace for 6 hours, we were growing raisins into dates. The precipitates became too large and the material was weakened. We got way past this peak right here. And so I had to go in there and say, okay, guys, let's do some experiments and let's figure out how long this motor housing can really sit in there before we start having a degradation in strength. And we did a bunch of experiments where we left this motor housing in the furnace for 5 minutes, 10 minutes, 20 minutes, 30 minutes, 40 minutes. And we took hardness tests to figure out when the material was beginning to soften. And it turned out that it was really only good in there for about 12 minutes before it would start softening. So they cleaned up their act. They put in controls in place so these things would never stay in the furnace more than 12 minutes. So how does this happen? What is the mechanism that's at play? Before I go there real quick, just again, precipitation hardening. This is a tool we have. This is a tool that material scientists can use to maximize the yield strength to density ratio. So how does this work? There's a theory called the Orwan bypass theory of dislocations that describes how this mechanism works, why these materials become stronger, or why they become weaker, why they become stronger. So on the left here, I've very carefully tried to draw up two different situations of precipitates and lattice, okay? On the top here, this is a coherent precipitate. So the blue is one species of atoms, the gray is another species of atoms, the purple is yet another species of atoms. And right in the center here, we have a precipitate. Okay, this precipitate is a coherent precipitate because as you see, the atomic planes line up with the atomic planes in the precipitate. Okay, this is a coherent precipitate. Because these atoms aren't the same, there's sort of a strain, what's called a strain. There's some distortion in this lattice of atoms that makes it difficult or makes it more painful, requires more energy to move a dislocation through this region. As a dislocation moves through this coherent precipitate, it'll actually cut through this precipitate. And it takes energy to do that. Depending on the size, it takes more or less energy. On the bottom here, we have an incoherent precipitate. So I've actually done a pretty miserable job of drawing this because this really probably should have been drawn bigger. But as you see, the precipitate should have been bigger. But as you see here, this is the precipitate, and none of the atoms really line up very well. It's an incoherent precipitate. It's its own little island. It doesn't match up with any of the planes in the aluminum. So when a dislocation comes through this region that has this precipitate in it, has this incoherent precipitate, it doesn't actually cut the precipitate. It sort of wraps around it. And that, depending on the size, can require less energy than cutting it. Right down here, I have a transmission electron micrograph that actually shows what this looks like. This is a real material. I don't actually know what material, but this is a real material. And these little squiggly lines are dislocation lines. And in many cases here, you can see these little loops. Okay, well, I could probably make this a little better. Can do this. You guys still see this? Sorry, I should have done that earlier. You can see these little loops right here, okay? And inside these little loops are little incoherent precipitates. They're too small to see with this magnification, but they're there. And that is what happens when a dislocation comes through a region that has an incoherent precipitate. Now, depending on the size, either one of these can require more or less energy to move that dislocation along, which of course translates into a different, better or worse yield strength. And starting off at very small sizes, you're more likely to have a coherent precipitate. And when the dislocation comes to that area, it cuts, and that's this curve here. As it grows, it'll lose coherency and become incoherent, and then you end up with this with the loop. Okay, and the loop at bigger grain sizes or bigger precipitate sizes can take more energy. So the net result is that there's a critical size, there's a critical precipitate size right here, a critical precipitate size here where you get the maximum amount of strengthening. Okay, this is a really critical point. You have this piece of bread, you've got these raisins in it, you're growing the raisins. There's a critical point. You're growing these raisins through tempering, or heat treating. There's a critical point where these precipitates get too big, they lose coherency, and you don't get as much strengthening out of them. Okay, so just try that again. When you're below this line, when you're to the left of this line, there's a precipitate size. It takes less energy to loop if the precipitate is incoherent. Okay, where's my cursor? Right here. When it's coherent, it takes more energy to get there. But as you get to a bigger grain size or bigger precipitate size, the particle loses coherency, and it takes less energy to move this dislocation through the region. So the material's not as strong. Okay, so the critical size is important. And that's how you design a heat treatment. That's how you design a heat treatment that you get so that you get the strongest material. You find out what that critical size is, and you make sure that you don't grow your particles past that. Another tool that the material scientist has at his or her disposal to increase the strength to density ratio of a material is grain size. There's what's known as the Hall-Petch strengthening relationship, and it basically says that the strength of a material, the yield strength of a material, is inversely proportional to the grain size to the half power. So what this means is that the smaller grain size you have, the higher the strength increase. And there are some ways of taking a material and making sure the grain size stays large or stays small. The reason that this works is, I think, a little theoretical, but the best I understand it is that, did you have a question there, Wu? Oh, I thought you had your hand up. No, okay. The guys, stop me if you got a question, remember, okay? It takes energy in order to get a dislocation to hop over a grain boundary. That energy equates to higher strength. So that is one theoretical explanation of the Hall-Petch relationship. Now, material scientists do have tools at their disposal to stop the grains from growing. Okay, stop the grains from growing under a lot of conditions. Niobium, for example, is used as a very potent grain refiner, make the grain small and steel. There's ways to pin the grain boundaries so they don't grow with precipitates. There's ways to paint, called painting the grains with materials so they don't grow. One of the professors in your department, in the material science department, Professor Chris Hsu, started a very wonderful company where they found a way to make nanocrystalline nanocrystalline nickel by painting these grains with a tungsten solution. So you can imagine a little grain of nickel, and then it has almost like a monolayer of atoms over it of tungsten that make it thermodynamically unfavorable for this grain to grow. So that's how you can preserve the grain size, because grains grow with temperature and time. So for example, when I was a graduate student, I had a friend who was doing research in nanocrystalline nickel. And what this guy did was he used heat to vaporize nickel, and then he had a cold finger, like a little chilled kind of copper little finger, and he found a way to put these two in the same chamber in a vacuum. And then as the nickel evaporated, it would get close to this, this cold finger, this copper cold finger, and then the nickel particles would freeze instantly when they hit this cold finger. Okay, and then they would freeze in this tiny little size here, this tiny little grain size. Okay, and so on Monday he was very happy because he took a hardness test, and he went up and told his advisor Julia Wertman, "Look, we got a 5 times increase in strength out of this nickel." Julia got all excited. Professor Wertman got all excited, but then they measured it again on Friday when Professor Wertman came back in the lab and wanted to see see the actual hardness measurement. Found out the material wasn't strong anymore. And what had happened is that because there's energy associated with grain boundaries, and materials shift in directions to minimize their energy. The grains grew, and the material was no longer strong anymore. It was back to being like normal, ordinary aluminum. So that project didn't work out very well. I think eventually my friend Brian figured out how to solve the problem with pinning the grains or something, but making small grains and preserving them at high temperatures, or even room temperature sometimes, is a challenge. And it's something I think that's only recently been solved by Professor, well, I mean, of course, there's niobium, there's grain pinning, that's happened forever, but in really to make them stable at higher temperatures, I think that's sort of a new invention that's been recently developed by Professor Chris Hsu in the Material Science Department, and you can go read some of his papers about how he does this. They're very deep in thermodynamic theory. So bring a cup of coffee and some patience. Okay, another tool that we as material scientists have to strengthen the strength-to-density ratio of materials is phase selection. When you get an ordinary piece of steel from a steel mill, it's typically made up of ferrite and pearlite. It's a body-centered cubic structure. This material is not weak; it's got some strength. But through a heat treatment process, which we're going to go through in the next slide, I think, you can transform that ferrite and pearlite BCC material to a martensite material, which is body-centered tetragonal, which is much stronger. And we've talked a little bit about martensite in previous slides. We talked about this interlock of these needles and how it's hard for materials or for cracks to propagate through those little needles. It's also difficult for dislocations, obviously, to move through those little needles, and that comes back in some sense to this Hall Petch strengthening, in that you have all these little tiny, strong little whiskers and fingers that are nanometer sized or maybe micron or a couple microns in size. Okay, and because they're so small, it's difficult for dislocations to move from needle to needle to needle. So that's why the martensite material is very strong. Forming composites. Carbon fiber polymer composites have become much more popular, certainly since I was a kid. We see them in all kinds of wonderful places. Bicycle frames, racing bicycle frames. Carbon fiber epoxy has revolutionized the bicycle industry by making stiffer, lighter bikes because they're able to provide material that has a higher strength to stiffness, strength to density ratio. So you form a composite, of carbon fiber is typically, when it comes to bicycles and a lot of high performance structures, is typically a polymer with a bunch of fibers that man put in there. It's a synthetic structure. It's a synthetic precipitate, if you will. So you've got this epoxy, and you've got this woven, or maybe it's not woven. Maybe it's a bunch of fibers that are all going in the same direction. You've got a zillion of them all kind of there, facing the same direction. You fill this up with epoxy, and you let the epoxy cross-link and cure to form a network, and then you can very effectively transfer load from the matrix to these fibers. And that produces a very strong material at a low density. And the strengthening of that material is given by this equation here, the rule of mixtures. It basically just says that you can relate the volume fraction of the amount of fibers to the strength of the material. That's basically what this equation says, the law of mixtures. Now, composites don't always have to be made with a polymer. There certainly are metal matrix composites. There certainly are ceramic matrix composites. So I want you to realize that there are other things besides other composite materials besides just polymers and epoxy and carbon fiber. I remember when I first started graduate school, I was talking to a professor in the department at Northwestern where I went to school, Professor Morris Fine, and I mentioned about metal matrix composites, and he got all upset. And he was a very experienced metallurgist who'd been doing it for decades and really knew what he was talking about. And he said, "Oh, come on, Don, it's nothing but a synthetic composite. It's nothing but a synthetic precipitation alloy about making metal matrix composites." Because all he was trying to say is that in one case you've got nature that grows these strengthening elements on its own, which is kind of elegant and beautiful inside a matrix of material. In the other case, you're a human, that you're putting these little fibers in there or little precipitates in there, and that's synthetic and maybe not quite as honorable, I guess, from his perspective. In either way, they both can be used to make materials that have higher strength to density ratios. Back to this fundamental paradigm of material science the processing, structure, property, performance relationships, and that the fact that the processing, structure, and property, these all have their subsystems as well. The processing has there's many different types of processing methods you can do. There's different structures. You want certain structures that give you certain properties. You have to choose the processes that change the material in a certain way to give you these different microstructure properties, and then that different microstructures which give you the different properties you want. So we're focusing in, of course, on strength to density ratio. And now that I've shown you about 4 or 5 or 6 different strengthening mechanisms, these different subsystems, these different tools that we can use, that material scientists can put in place to strengthen a material, we can now plug those into this paradigm, this processing structure property paradigm. We can plug that into this diagram that has the three chain links and the subsystems. So the next obvious, so we've plugged those in here. I've plugged in, solution strengthening. I've plugged in Hall Petch. I've plugged in precipitation strengthening. I've plugged in transformation. These are the microstructures that we potentially want to use in order to increase the strength to density ratio of this material. But how do we get there? How do we get there? What is the link? What is the link? What are the methods? How do we go from, what processes will get us these structures? What do we do? What are the processes we can use? What are the systems of this process that we can use in order to get to those microstructures? And that's what I'm going to talk about here. So I'm going to start off with steel here, okay, because the strengthening or the processing, the link between process and structure in steel is very well understood. In fact, it's probably better understood for steel than any other material we know of. We know more about steels than we know about aluminum. We know more about steels than we certainly know about nickel-based superalloys or titanium alloys or cobalt-based superalloys. We know a lot about steel, and that's why it's a very popular material. I think Professor Eager has spoken a couple times to you guys on this about the popularity of steel and why there's so much of it around. So the heat treatment process for steel isn't that much different than what I showed you for aluminum. At room temperature, a non-heat treated steel is this BCC, body center cubic material, with ferrite, for example. When you heat that material up above, say, 850C or 800C, depending on the composition, sometimes 900C, the body center cubic material will transform to a face center cubic material. It'll form what's called austenite. Okay, it's called a solution treat. Okay, you're forming a solid solution. It has a face center cubic structure. Okay, and that is stable at high temperature. If you let this steel cool down slowly, very slowly, it'll turn back into ferrite. Okay, if you quench it quickly, the carbon atoms don't have time to diffuse to the BCC lattice locations. They get stuck in position, and you end up with a material, like I said, called martensite. Now the martensite looks like this right here in the middle, this one right here. Okay, that's what it looks like. I showed you a better picture before. And this martensite is very strong. It's very strong, but unfortunately it's brittle. And if you have a high rate of loading on it, it'll crack even before it hits the strength at which it would normally hit if it were being loaded at slow rate. You've probably seen this with cheap kitchen knives or cheap razor blades that they chip. They chip and then they're not that useful anymore. I'm just keeping track of the time, you guys. They're not that strong anymore. And that's a problem. So as an engineer, your goal then is to determine how do you decrease the brittleness of this martensitic steel. And you use an intermediate heat treatment, okay, called tempering, where you form what's called tempered martensite. And to a large extent, there's some other phases that are precipitating there. The little martensite needles are getting a little bit bigger. They're coarsening, they call that, with the temperature and time, which can increase the toughness of the material, sometimes substantially, but it increases the strength of the material, or the toughness of the material, which is important. You can have too much strength and end up with too little toughness and be in trouble. In certain alloys of steel, where you have a lot of alloy content, you can also precipitation harden the material. So in addition to having the martensite, you can also have precipitates in there, like combinations of metal and carbon called metal carbides. An M2C carbide, for example, is a very potent strengthener of steels. And knowing how to do this heat treatment, knowing how to do this tempering step so that you increase toughness and increase strength is one of those things you're really trying to do here. You're trying to increase strength because you're trying to increase strength to density ratio. That's what you need, the material you need to create in order to form a lighter structure. So how do you do that? So here's one example. This is from Professor Olson, who's also at MIT, by the way. And this is an example for an alloy developed by the Air Force called AF1410. It's got a lot of cobalt in it. It's got a lot of nickel. It's got a little bit of carbon. Okay, and let's just say that for the purpose of argument here, we can manipulate the amount of moly and amount of chromium. This alloy is a precipitation hardening steel. So not only can it be martensitic, but it can also have precipitates in it that stop those dislocations from moving, make it require more energy in order for the dislocations to move, which increases the strength of the material in the far field, where you're going to use it as a structural engineer designing a bicycle frame or a bridge or an airplane fuselage. Shown here are two graphs of what's called driving force. Okay, so driving force for a phase or precipitate is a kind of an abstract topic, and it's something that over years I think I've developed the ability to understand it. Initially, I was dramatically confused by it. I didn't understand it. I didn't believe it existed. Whatever you want to call it, I thought maybe it was dogma. It is real, but what it is when you have let's say you've got your bread. That's a bad example. You've got your matrix of steel, and you want to, or aluminum, and you want to precipitate out these little particles. There's energy associated with that. There's energy associated with that. As you heat this material up, the driving force for these little precipitates to grow out of the material increase. It's very similar, I think, to rain. As you get more and more moisture in the atmosphere in a cloud, as you increase the atmospheric pressure, little water droplets, there's a driving force, little water droplets precipitate out of this cloud and then fall to the ground and get your car all wet. That's a driving force. The same thing happens in steels and aluminums and nickels and titaniums. You have this driving force that causes these little particles to precipitate out. This driving force is what helps you predict when you're going to get those precipitates and when you're not, and when you're going to get good ones and when you're going to get bad ones. Just absorb that for a second. It's this driving force. When designing a material, you get as I've just described already, you get the highest strengthening when you have pretty small particles, pretty small coherent particles. The more of these little small particles that you can put in your overall piece of material, the stronger it's going to be, because it's going to take more energy to move that dislocation past lots of little precipitates than a small number of big precipitates. The way to predict whether you're going to get that fine distribution of lots and lots of small particles is by knowing the driving force energy to precipitate out those particles. These two graphs show that precipitation energy in kilojoules per mole to precipitate out those different precipitates. On the left here, the green, these are to precipitate MC6 carbide precipitates, and these are incoherent. The atomic planes don't line up. On the right is the driving force to precipitate the coherent M2C carbides. They're really good strengtheners. They're very potent strengtheners. And these lines are constant thermodynamic driving force lines. They're contours, okay? Now, in the Steel Research Group at Northwestern University, they did a lot of experiments with this AF1410 alloy where they added molybdenum and chrome. And they took compositions along this orange line, or almost looks yellow, this yellow line right here. And then they took strength measurements, and they looked at the microstructure, and they looked at the atomic level with transmission electron microscope to understand if the particles were MC6 or M2C carbides and whether they're incoherent or coherent. And they found that as you got to a driving force, as you got to a composition that led to a driving force, of 15 kilojoules per mole, you would start forming these M6C carbides, which were incoherent and would not very effectively strengthen the material. So that made them realize that you need to pick a composition that doesn't get you past this point right here. This point right here where you would get above, see my cursor is right where this yellow and green line cross. You don't want to get to the right of this point. You want to stay to the left of this point in order to avoid precipitating these MC6 carbides. Now, looking on the other side here, on the right side, this is the driving force for the M2C carbides, the coherent carbides. And what I've done, or what the Steel Research Group did, is they transposed this 15 kilojoule per mole line onto this graph here, and that's this green line. So this green line right here. I lost my thing here. This green line right here that says 15 next to it. All I've done is I've moved that over here. That's this line right here. Make sense, guys? Give me a thumbs up. You want to stay to the left of this line, right, to make sure that you don't get MC6 incoherent carbides. But you want to maximize the driving force energy to form the M2C carbides, the coherent carbides. So that means on this graph, you want to be as far as you can to the right. So what is the point that's along this green line, okay, that doesn't go past this green line, doesn't go to this green line, but it gets you to the highest driving force for precipitating the M2C carbides. And that's, if you look, that's this contour line right here that says 19 kilojoules per mole. So this composition right here, it's like 1 1/4, maybe 1 1/3 weight percent molybdenum, and about, I don't know, 2.25 or 2.3% chromium. That becomes the composition that you choose to precipitate out a fine dispersion of M2C carbides, yet avoiding precipitating out in your steel the M6C incoherent precipitates. Okay, so you see what just happened, I hope. This is a situation where I've actually, or the Steel Research Group, they've actually found a composition, and by choosing that composition, you've engineered in a certain microstructure. You did this heat treatment, that was your process. You precipitated out what you wanted, that's your structure, that gave you the strength. You've done that processing to structure link. You've engineered that link to get the microstructure that's going to give you the highest strength to density ratio. See that, guys? See that? Thumbs up, somebody, everybody? Okay. Steve?
Yeah, I got it.
Thumbs up. So this is really where it is. This is really engineering a material rather than just picking properties out of a table. You've really engineered here. Now you can go back and you can, if you've got the right furnaces and vacuum equipment and refining equipment, now you can go back and mix up cobalt, nickel, a little bit of carbon, and you know the exact amount of moly, the exact amount of chromium used to engineer this material to have the maximum strength to density ratio. Of course, I should mention this. The density obviously doesn't stay constant, right? Because as you add chromium and molybdenum, you're going to increase the density because those items have, I think those elements have a higher density than steel. So there's probably an optimization problem here. You know, where do you start increasing the density? Where do you start, you know, where do you maximize the strength? What's the density at that strength? So there's probably an optimization problem here. But if you weren't so worried about that, this is, you know, right here. This is what would give you the strongest material.
Can I ask a question?
Absolutely.
And it has to do with this designing and the heating and quenching process. How do you introduce the what's it called, the martensite? Is it the medium that you quench it in?
Sure.
Does it matter what medium you used? I mean, can this design process be affected by whether you use water or whether you use some other material? Can that affect this design?
Absolutely, absolutely. So this is a question that I'm going to exploit to talk more about the link, okay? Because There are steels that will form martensite when you quench them in ice water. There are steels that will form martensite when you quench them in room temperature water. There are steels that will form martensite when you quench them in this gooey type of polymer. There are even steels that will form martensite when you let them air cool. So you quench them in air. And this is, I don't have all the details of this right in front of me, but this is part of designing the steel. You can pick compositions that will allow you to form martensite at room temperature. Here's a great example. You must know Reynolds 853 bicycle tubing. Sound familiar? Huh?
Yep.
Okay, so Reynolds is for the rest of you guys, Reynolds is a company that makes bicycle tubes. They're British, they've been around forever. They originally got into the business of making high strength tubing, I think because they were making oxygen bottles for Mount Everest climbers that needed a needed a light, strong, high strength to density ratio canister to hold oxygen so they could carry as much oxygen up mountainsides as they could possibly get. But the 853 alloy is an air hardening alloy, and it will form martensite, I believe, by air quenching. They call it an air hardening steel. So when you take a tube of Reynolds 853 and you braze it to it or weld it to another tube, it'll and Tom can help me with this because he's a welding expert here. You can solution treat, or you can turn some of that material in the weld zone to austenite, I think. And then if you quench it, it'll form martensite. If you air quench it with 853, it'll still form martensite. It's an air hardening steel.
But it's untempered martensite.
It is untempered martensite.
So you have to temper it afterwards.
One would think, yeah. I'm not sure if the real bicycle builders
Well,
do.
if you want the best toughness in your weld zone, yes. I'm not sure the bicycle people are worried about that. Now we're getting to the question of the plastic zone size in fracture mechanics. That's another topic.
Sure. Do you, am I right? Can you form austenite in a weld?
Oh, yeah, yeah. In fact, we call it MA constituent, martensite austenite. It has its own acronym nowadays in welding.
Okay. Regardless, the Reynolds company in England has done more for bicycle steel. Well, I won't say that. They've done a lot for bicycle steel. They've come up with some very interesting alloys. They've come up with alloys very similar to this AF1410, the martensite aging steels that strengthen by being martensitic and also by having precipitation hardening. They've formed a stainless steel version of that, so you don't have to paint your steel frame anymore. I'll probably talk a little bit about that later in the lecture. And then their competitor is an Italian company called Columbus, and they've spent a lot of time focusing on grain size, on minimizing grain size through alloying with niobium. And they even call their steel like what do they call it, Steve? They call it like Nioba Max or something like that.
Yeah, I sent that in an email to the other day. It's Nioba. I can't even pronounce it. It's Nioba.
Nivachrome is the alloy. Nickel, vanadium, chrome. Yeah. But I know if you look at their literature, if you look at Columbus's literature, they talk a lot about adding niobium. They just don't tell you that they're doing it to keep the grain size small.
So is the martensitic quality or degree a function of how these materials cool? Because blacksmiths have been cooling in water for like 3,000 years.
Right.
And then, the Japanese discovered that you can cool in oil, and that cools more slowly, and that affects the martensitic quality. Is it the medium that you use that right. controls the martensitic quality?
Yes, if you cool too slowly with certain alloys, you'll go back to ferrite, which is weak and soft. So you got to cool quickly. This is disgusting, but there's even crazy stories out there about how blacksmiths used to round up slaves, and they thought for some reason blood. They would quench in blood, so they would take these poor slaves and they would stab them. As that was their quench, they would use their blood to quench the steel, and they had some voodoo dogma belief that would give them higher strength. I don't know what the heat transfer, the thermal conductivity of blood is versus water, but I bet they're pretty close.
Actually, blood is saline, salt water.
That's true, but what does that mean for the thermal conductivity?
Well, it's a better quenching medium. It's not oil. It's sort of But it's better than pure water.
So maybe if they were using pure water at one point in history and they weren't getting high enough cooling rates and weren't getting a high enough amount of martensite, or maybe sometimes when you quench martensite, you can get what's called retained austenite. So some of that FCC austenite that existed at the high temperature. Okay, sometimes that doesn't completely turn to martensite. Sometimes you're left with some of the austenite, and what happens is when a crack hits that area, the energy associated with the crack tip can then transform that austenite to martensite in situ as the crack hits it. And because there's a volume change associated with that, the martensite actually has a higher volume than the austenite atomic cubic cell. What that does is it clamps down on the crack tip, and you can effectively shield the crack tip and increase the toughness of the material. So that's a topic I wasn't going to get into, because now you're talking about toughness to density ratio.
Right.
But we can talk about it some more offline if you're interested. Anyway, I think we're going to have to stop here today because it's 9:58. You guys have the same time I do? Yep. So I think we're going to have to stop here today. Are there tomorrow, or not, I'm sorry, next week we'll go on to talk a little bit more about these precipitates and different sizes and ratios and the number and how that affects hardness and how you can design those in by choosing compositions. And we'll present more data from thermocalc. And by the way, I forgot to mention that this data here, these driving forces, you can get this type of information from a program called thermocalc, which is a thermophysical chemical materials program and database that is now available in the material science department.
It's written by the Royal Institute in Stockholm by Matt Sillert, who was one of Morris Cohen's postdocs at the same time Larry Kaufman was.
Oh, is that how it happened?
So
okay.
Hillert and Kaufman are the two great world gurus on calculation of phase diagrams.
And driving force.
They were postdocs with Morris Cohen at the same time in the early 1950s.
Okay, but that driving force came out of that as well, not just phase diagrams, but driving force as well.
Right.
And that's what we're using here. So this data, these driving force contours, these came from this research that Professor Eager mentioned.
Right. But it all started with Carl Wagner in the early 1950s when he came from Germany to MIT.
I'm going to look this up.
Thermo.
Carl Wagner, okay.
Wagner. It's German Wagner.
Alles klar.
Okay.
Any questions, anyone? Sheng Hong?
Don or Tom, real quick, the slides you were presenting, I don't think they are the same as the ones on Stellar site. Would it be possible for us to get them?
Yes, I will get a copy to. Is Jerry still around, or is she
Jerry's still around.
Is she going to be around?
She will officially as of I think March 11th or 8th.
I will send these. I'll send these to Jerry, and we'll try to get these posted. The problem is that some of this is evolving with time. I spend hours over the weekends trying to clean this stuff up, and so that's why I haven't given it to her, because I'm still working on it to some extent.
You changed the thermodynamic data by 1%, and these curves can change.
That's right. That's right, and that's why you can put a little bit different cobalt in here, for example. And these curves change dramatically. So that's the fun of this. That's the interesting complexity of this that makes it interesting, is that these different compositions come together to make these minute changes, but they get a big changes in how the material strengthens or doesn't strengthen.
Right. Cobalt is the only element in the periodic table that raises the martensite temperature. Okay, the martensite start temperature.
Okay.
That's why it's so much of it in AF 1410 and some of these other high toughness steels. Like
Airmet 100 has a lot of cobalt too, but doesn't the cobalt also form very, very nice M2C carbides?
I don't know. You'd have to ask Greg that.
I think it does. I think I remember him telling me that long ago.
Okay. Okay, we ought to shut down here soon.
Okay, so I'm going to stop sharing.
Thanks.
Thank you, Don.
You're welcome. And I'm going to stop the recording.
Thank you.
You're welcome. You. Cheers, guys. Tom? How's it going, Steve? I like the bike you sent me.